So today we're moving on to giving you more restrictions. Yesterday you were just
That's not nice.
Basic counting, figuring out how many ways you can order things, but we're going to put in some different things. So permutation, determining the number of ways of n elements can be arranged in order. So the big thing about permutations, they are in order. Order matters. So if I ask you how many ways can I make a group of 3 people? Well, that would be
12.
well, and here we have 1, 2, 3, 4, 5, 6, 7. How many ways we could make a group of 3 people? It would be 7 times 6 times 5, correct? Because there's 7 people to choose for the first one, 6 for the second, 5 for the next, right? Mm-hmm. So that would be, 30? So 110 different 3 people groups we could make. Okay? But what if I now said that in that group, you can be assigned a specific thing? Like you could be the recorder, you could have to go get stuff, you could be the speaker. So there's things like that. So that matters, doesn't it? It's not just a group of 3 people. Once I'm in that group of 3 people, then I could be 3 different things, couldn't I? So it changes it. So a permutation, an ordering of n elements in the first, there's a second, and a third, and so on. Order matters. That's what I'm going to keep saying. So when you read a question, you've got to decide, does order make a difference here? So what it is basically, I told you yesterday, it says the permutation of n elements is 4, 3, 2, 1, which is the factorial, which I told you about yesterday anyway, right? Mm-hmm. Okay. So now it just has a name. Tell me when you're good.
Good.
Okay, so how many permutations are possible of the letters A, B, C, D, E, F? Now I could write them all out, but would that be a pain? Yes. So when I say, how many ways can I place? So we have 1, 2, 3, 4, 5, 6. And I've done that every time you've had a question, right? And I do that in my work. It just keeps my brain straight. So how many choices do I have for the first one?
6.
6. The next one?
5.
Next?
4.
3, 2, 1. And so I multiply those all together. And so we got 6, 24, 120, 720. Did I multiply that right? 120 times 6 would be 720.
Yeah.
So 720 different ways. Remember that a permutation order is important. So the permutation A, B, D and B, A, D are counted as different because order of the elements is different. Okay.
Okay.
We good, Savannah? Okay. So 8 horses are running a race. How many different ways can these horses come in first, second, and third? And assume there is no ties. So we got first place, and I touched it. First place, second place, third place, right?
8, 7, 6.
8, 7, 6. So 42 times 8, so 6, 32, 33, 336 different ways they can get first, second, and third. Are we good? Okay, so now we actually have a formula, and it is NPR, N permutate R. It is the number of permutation N elements taken R at a time. And again, what matters? It's a permutation, what matters? Order. So this is n factorial over n minus r factorial. So you have to do your subtraction first. So kind of similar to the choose formula that you saw the other day, right? So 8 horses are running a race. How many different ways can these horses come in first, second, and third? Assume there's no ties, so let's do it with this formula, okay? So what's my n? 8. So it's, oh, and I touched it. So it's 8 permutate, and we want first, second, and third, so how many is that? 3. So n factorial, so 8 factorial over 8 minus 3 is 5 factorial. So remember when I'm done, because it would be 8, 7, 6, then 5 factorial, right? So I'll draw 8, 7, 6 times 5 factorial and over 5 factorial. So those reduce. So what do I get again? 336. So could I use either one of those ways to do this problem? Yes. Because what mattered? Order. Okay, distinguishable permutations. Now, this, to me, the definition does not really make sense. So I would put distinguishable permutations, and then after we do the example, I'd write some notes on the example. Does that make sense? Because when I read this, I can get something out of it, but most people cannot. Okay, it says, suppose a set of n objects has n sub 1 of one kind of object and n sub 2 of another kind of object. Repeating things, okay? So distinguishable permutations means I can't use, let's say a word has 3 W's in it. A W is a W, and it doesn't matter if it's the first W, second W, or third W. Make sense? So what you do is you put the number of things you have, total, factorial on top. I touched it again. And on the bottom, you put how many of each factorial there is. Okay, so how many distinguishable ways can the letters in banana be written? So how many letters are in banana?
6.
6. So it's 6 factorial over. And just go down the word. How many B's are in banana?
1.
So it's 1 factorial. Times. How many A's are in banana?
3.
3. So it's 3 factorial. How many N's are in banana?
2.
2. So it's 2 factorial. Now does that definition make sense?
If you rearrange the letters, it wouldn't be banana anymore.
You're right. It didn't say banana. It just says how many different ways can you group the letters. Okay, so we have 6, 5, 4, 3 factorial. Why did I stop at 3 factorial? because I have a 3 right here, right? So the 3's factorials can reduce. Why didn't I write 1 and 1 on the bottom? Because it doesn't matter, right? You want 2 into 6 or 2 into 4?
4.
Okay, so 10 times 6 is 60. Now, those are distinguishable, right? Meaning if it's an A, it's an A. It doesn't matter if it's the first or the second. If I didn't say distinguishable, it'd be 6 factorial, which would be 720. Because we've done 6 factorial several times, haven't we? Is that a huge difference, 720 to 60? Yeah. So, like, good words to do this with would be like Mississippi, right? Because you'll have lots of I's and S's.
1.
1.
Word. Yeah.
Okay, am I good?
Let's do that.
You probably do it in your assignment. My luck. In the book, it has all 60 combinations if you want to write them out.
No.
You don't think that would be fun?
No.
Oh, they don't have it. Do you guys want to do Mississippi?
No.
Why not? So Mississippi. How many letters are there?
This makes a PP.
Shut up.
There's 1, 2, 3,
11. I got 11. So 11 factorial. Then just work across. How many M's?
1. 4.
So 4 factorial,
4.
4 factorial,
And 2.
and then 2.
Wow.
So then it's going to be 10, 9, 8, 7, 6, 5. And get rid of one of those. So 4, 3, 2, and 2. I said we get rid of 8 and 6.
Okay. We need 50 times 9, which is 450.
Times 10 would be, right?
Times 7.
Oh, we forgot the 7. How about 63 times 5? That'd be easier, wouldn't it?
No.
So 63 times 5 would be 5.
310.
No,
I don't know.
15. Times 10.
15 for 3,000.
So 3,150. See, that was fun. You understand that, though? Okay.
Yeah.
Okay, good. Combinations. Order doesn't matter. Have we done combinations already?
Yes.
Yes. Now, a combination lock is different from combinations of things. On a combination lock, does your order matter?
Yes.
Yes. So you would use a permutation. You would not use a combination. Different kind of combination. Okay? So, in a combination, ABC is the same as BAC. The group does not matter. We're just sitting in a seat. What other group would be exactly, like what other groups would be the same? ABC, BAC, ACB wouldn't be counted. What about CAB wouldn't be counted? CBA, BCA,
This is what we did last year. ACAB.
okay. So I have 1, 2, 3, 4, 5, 6 different ones, and all they be counted as how many times?
1.
1. So are you going to have less combinations than you would permutations?
Yeah.
Yes. Your numbers will be smaller with those. Okay, how many different ways can the 3 letters be chosen from the letters A, B, C, D, E? The order of these letters is not important. So combination or permutation?
Combination.
Combination. So how many do I have total?
5.
5. Choose. How many you want? How many are we choosing?
3.
3. Now you got to remember the formula. Remember what goes on top? N.
Also 5.
So 5 factorial over 2
2 factorial.
factorial times 3 factorial. So then we'd have 5, 4 over 2. So 2 is 10. You guys get 10? Okay. So n choose r is n factorial over n minus r factorial, right? What is npr?
N factorial.
No, but it's n factorial over n minus r factorial. So if you think about this mathematically, in the combination, I'm dividing by a larger number than I'm dividing by in a permutation, aren't I? Because I have this extra r factorial there. So that's why it makes fewer when you're doing a combination. So do you have to know both of those?
Yes.
Yes. Am I good?
Yeah.
Haha, there it is. Okay. A standard poker deck. Do you all know, have you all played cards with real cards?
Yes.
Everyone in here? In years past, I've had people in the room that have never touched cards. Like, oh my gosh.
What kind of cards?
Like playing cards. You know, there's 4 suits,
Yeah.
right? There's 4 suits. How many cards are in each suit? 13. There's 3 face cards in each suit. What's a face card?
King, queen, jack.
Queen,
Joker.
king, queen, jack, not joker. Joker's not counted. They have faces on them, right? Okay. So they do have that in the book because some kids don't even know them, and I can't even fathom that. So a standard poker hand consists of 5 cards dealt from 52. How many different poker... What?
What are you reading?
What's on my screen?
No, it's not.
So what's on my screen?
So it's on our screen.
What's on my tablet and what's on my computer are 2 different things also.
No way.
A standard poker hand consists of 5 cards dealt from 52. I wonder what it was recording. It was probably recording what was up. I don't know. How many different poker hands are possible? After the cards are dealt, the player may reorder them so the order isn't important. Okay? So we've got 52 because that's the total, right? Choose how many? 5. So 52 factorial over 47 factorial, 5 factorial. Well, at least it's a decently sized number, right? So 52, 51, 50, 49, 48. What? Yeah. 5, 4, 3, 2. Well, 8 goes into 48, right? 6 times. And then 3 goes into 6 2 times. How about 5 into 50? And then you would have to multiply that out. Do you need a calculator to do that? You don't have to have one. Would it be nice to use one?
Yes.
Yes. So you can use one.
Wait, what did you?
Would you put the
Yeah,
4 times 2 is 8. Yes.
I can do that.
4 times 2 is 8. Yeah, because it's all multiplication.
We did all of the last question.
So 4 times 2 is 8. 8 goes into 48 6 times. And then 3 goes into 6 twice. So 52 plus 51 plus 10. Not plus. How about multiplication? 52 times 51 times 10 times 49 times 2.
2,598,160.
I think that's what I got. Yep. 2,598,960 different poker hands that you can get.
Oh yeah.
That's a lot.
That's it?
Why are you
That's
teaching
it.
us poker in school?
I don't think I taught you poker.
That's like, isn't it like impossible to get like the same, deal like the same 5 cards
It's
twice?
not impossible.
It's really unlikely.
Well, it's not probable. It's not impossible because barely anything is impossible, but it is not probable, like to deal the exact same hand. Like you mean in the same game, like in the same.
Yeah.
Yeah.
Like over your lifetime, it's gonna be really hard to do that.
Well, it depends how much poker you play because there's only 2 million,
Blade's gotta play a lot.
2.5 million. So I guess if you play a lot of poker, then the probability increases.
Blade, you have to play
Is
poker
it
until you
possible for Riley to
The
float
same-
into the
I
air
got
and never
really
go
lucky
back?
and got it twice in a row.
Well,
I wish.
it is very highly improbable.
Yeah.
Okay, so you're forming 12-member swim team, 10 girls, 15 boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? So how are we going to do that?
Hold on.
Okay.
Yeah, and then one person's left out.
I don't know.
Active game.
Okay, can we do these at one time? No, because we have 2 different things, right? So do you want to start with girls or boys?
Girls.
Girls. Okay. So how many girls do we have? 10 girls. So we're 10, and does it order matter?
No.
No, just the choosing them, right? How many do we want? 5? And then it's probably going to be times, don't you think? Okay, how many boys do we have?
15.
15. And how many do we want on the team?
7.
7. So we have to do both of those things and multiply them together. So we have, 10 factorial over 5 factorial, 5 factorial? Times 15 factorial over 8 factorial, 7 factorial? Now, these are fractions, and it's multiplication, so I can make this just one big fraction, can't I?
Yeah.
And anything can reduce out anywhere, can't it?
Yeah.
Okay, so I'm going to do with the 8 factorial with the 15, so that would be 15, 14, 13, 12, 11, 10, 9. And I'm going to do the 7 with the 10, so that would be 10, 9, 8. Does that make sense why I did those the way I did?
No.
Yes.
Yeah.
Because I just took the bigger number with the bigger number. And then I have 5, 4, 3, 2. Well, I was going to write 1 again. And 5, 4, 3, 2. I tend not to put my dots in between them. I just know their multiplication. So what do you want to reduce out?
2015.
So we could do 5 and 3 and get rid of the whole 15. What about 3 and 4? Get rid of 12.
5 and 2, get rid of 10.
Oh, but 10's an easy one. Oh, but we have 2 10s. 5 and 2, get rid of 10. No, 2 and 4, get rid of 8. Okay, so, and I also always write down, because when I'm looking at that, that's an awful mess. I write down what I'm going to multiply finally together.
Mine's not messy.
Well,
Well, do better.
I don't know. I'm horrible. I get it.
Mm-hmm.
So 152, 154, sorry. And 810 times 13. I get 1,621,620.
Yes.
You guys remember how to multiply by 11?
Yeah.
How?
4 times 11 is 44. Period.
Any 2-digit number but times 11. You separate the 2 digits. So the 2 digits are 2 and 5. And add them together.
Yeah, easy.
Any 2-digit number.
Easy.
So 9 and 8. 7 carry a 1. So 1,078. I think that might be it. No. Okay, before you start solving a problem, ask yourself the following. Is the order of the elements important? If it is, what am I going to use? Permutation. Are the chosen elements a subset or a larger set in which order is not important? Then I would use what? Combination. Does the problem involve 2 or more separate events? And that's the fundamental counting principle. So we can do basic things up to like combinations or permutations. We could have any number multiplied times each other depending on what we have. So when you read a problem, are you going to probably have to read it more than once? Yes. I'll switch it back, but I'm really sure that's the last one. Yep.
Wait,
I said I will switch it back.
I thought you meant to like where we just were.
No.